Copious amounts of chocolate consumption aside, Halloween is one of our favorite holidays here at NerdKits because it allows us a unique opportunity to scare children that knock on our door. Just like we did with last year's infrared theremin and our capacitive jack-o'-lantern before that, this year we put together a project that we hope will scare many children.
The idea of the setup is this. We use a magnetic switch, a NerdKit, and a set of computer speakers. The magnetic switch and USB NerdKit detect when the door has been opened. The NerdKit then waits a few seconds before playing a sequence of loud, scary sounds over the speakers.
Trick or treat.
The first part of the project is using the magnetic switch to know when the door has been opened.
For that, we went to our local electronics store and picked up this magnetic reed switch, commonly used for burglar alarms. Basically, one part has a magnet, and the other part has two steel pieces near each other.
When the magnet is close by, it causes the steel leads to move and touch, and when the magnet is far away, the leads do not touch.
If you get your ear close to the switch and listen closely, you can actually hear the contacts opening and closing when you move the magnet near it.
In terms of using it in your circuit, it's just like a normal switch. You connect one of the terminals to ground, and the other to your microcontroller pin with the internal pull-up resistor turned on. When the switch contacts close, they will pull the voltage at your pin down to 0, and when the switch is open, your pull-up resistor will pull the pin voltage up to a logic 1. All you have to do is detect the state of this pin in your code to know when to start off your scare timer.
A big part of this project is audio storage and playback, but before we can even discuss the problems with doing audio playback from a microcontroller, we need to first talk about what it even means to have a digital audio recording.
Sound is a pressure wave that moves through the air. Microphones take that pressure wave and turn it into a voltage wave, and if you were to connect your microphone to a computer and record the sound, your computer would take that voltage wave, sample it at different points in time, and store its value, thus ending up with a stream of numbers that represent the waveform. Here, it is interesting to discuss two things about how the wave is sampled. The first is the sampling frequency, which means how often the computer samples the waveform, and the second is how many bits of data you store per sample. How you choose both of these numbers has storage space versus audio quality trade-offs. Really good quality audio, like CDs, are sampled at more than 44,000 samples per second, with 16 bits of precision. But, since we're not looking to reproduce a symphony, recording sound using 8,000 samples per second at 8 bits per sample still gets us good audio. So, let's do a little math to see if we can store the audio on the chip. If we have 8,000 8-bit samples every second, it means that for every second of audio, we have a total of 64,000 bits we need to store. Our bitrate is 64 kilobits per second. The ATmega 328p microcontroller that we are using has 32 kilobytes of flash memory. Assume that about 6 kilobytes of those are used for your program to do its work, and another 2 are used by the bootloader. This means that we have room for about 3 seconds of audio. While that might be great for a brief scream, it's not enough for an evil laugh afterwards, so we need to get a little creative.
So far, we have only discussed directly storing the audio samples on our chip. However, in order to get more information on the chip, we need to compress the data. While there are chips out there that can take a common encoding like MP3 and decode it for you, we decided to use a method known as Huffman-Coding. Huffman-Coding lets us compress the data, but it's simple enough that we can understand and implement ourselves without using any extra hardware. So let's talk about Huffman-Coding.
Because our samples are 8 bits wide, there are a total of 256 different values that are possible in our audio stream, the numbers 0 through 255. These are called symbols because they are the smallest unit of useful information we're trying to convey from end to end. A main feature of a Huffman code is that it is a variable length code. This means that instead of all our values being the same number of bits, we are going to use smaller bit lengths to encode some of our symbols, and keep a Huffman tree that lets us decode the sequence of bits back to the original symbols. Let's look at this stream of numbers that might have come from our audio file, but instead, let's consider their 8-bit binary representation. This is 8 8-bit numbers that would have cost 64 bits to store. Instead, I could encode each of the data symbols with the following variable length codes. This would allow me to encode this sequence of 8-bit numbers with this sequence of variable length codes. And, using this tree for decoding, we can decode the sequence by just starting at the top and following the tree until we hit a leaf in the tree. 1 1 gives us 2, then 1 0 gives us 4, 1 0 gives us 4 again, 0 gives us 8, and so on. Notice two things about how I chose the codes for my symbols. First, I chose them such that no complete code is the same as the start of a different code. This allows me to build the decoding tree in a way that I can follow it down bit by bit to a leaf node and know when to stop. Second, I chose the symbol 8 to be represented by the shortest length code. Since 8 appears the most times in my original sequence, this gives me better compression since the most common symbol has the shortest code. This example did not do true Huffman encoding. What Huffman figured out was the optimal way to build the encoding so that you get the best possible compression by assigning codes to symbols in a smart way. However, with this simple approach, we were able to reduce the 64-bit sequence into just 13 bits. Now, this example isn't necessarily fair, since our sequence only contains 3 different symbols, but the basic idea is to take the symbols that occur the most often and replace them with your shortest code. Since Huffman encoding relies on the symbols being distributed in a certain way, it does mean that different types of data will compress very differently. Text, for example, can compress very well because some letters occur much more frequently than others. This is a problem for our sound wave, since for a normal audio file, the values themselves are fairly well distributed over the possible 8-bit range.
To make Huffman coding work well here, we have to apply one more trick. We take the first derivative of the signal, or really the difference between one sound sample and the next one, and encode that using a Huffman code.
To see why this works, we can take a look at the probability distribution of our symbols in a sound file, and the probability distribution of the first differences. The original signal has more values that occur much more often than the first difference. This is true because the amount the signal moves from one sample to the next is usually relatively small. So when we look at the first difference of the signal, you get a much narrower range of probable symbols and increase the number of times those symbols repeat. This makes our Huffman code much more effective. Note that taking a derivative is something we can easily undo on the other side by taking an integral, so we have not lost any information at all with this conversion. Implementing all of this was actually pretty cool. We have a bunch of Python scripts that work together to convert WAV files into C code. The Huffman decoder itself is a C function which is written by a Python script. If you are curious about how all of this works, check out the description and code we have made available on our website.
So now that we have the digital audio stored on our chip, we need to recreate the original analog waveform to send that out to our speakers. Here, we go back to a concept we covered in previous videos, pulse width modulation.
Since our microcontroller can only output digital values, we switch back and forth between high and low very quickly, so that the average over a certain amount of time is our desired output value. In previous NerdKits video tutorials, we have shown how we can vary the brightness of an LED, or vary the speed of a motor by varying the PWM duty cycle. In both of these examples, we got away with PWM easily because both of these are naturally very slow systems. Your eye and brain helped us smooth out the rapidly blinking light, and the mechanical inertia of the motor smoothed out the PWM signal driving it. However, for sound, our ears are capable of detecting changes over an extremely wide range of frequencies, generally considered to be up to about 20 kHz. To make sure we only hear the average analog value we're aiming for, and not the on-off switching of the digital PWM signal, we do two things. We pick the PWM settings correctly, and built a small analog circuit between the microcontroller and the speakers. For more about this, check out the project page on our website.
This project has not had its final production run yet, but field trials have done very well. We hope you have learned about how we can compress some types of data to fit on our chip, and about one more type of switch you can use with your NerdKit. For more information about our kits, and more videos like this one, visit us at www.nerdkits.com.